So before going to the problem itself, let me introduce a new concept of, or the intuition, or looking at the circuit and figuring out things by inspection. Okay, and let's do it for a common source amplifier with source degeneration. Okay, remember, it's a common source amplifier with source degeneration. So essentially you have a common source amplifier RD, and this is VDD, and you have V out here, and this transistor has some V bias plus some input voltage. This is a signal, V in is a signal. Okay, and so source degeneration, where I have some source resistance and this node is anyway not grounded. Okay, that is the idea. I have some source resistance, so this source will be degenerated, the gain will be degenerated, but this is anyway in incremental feedback. We know this, we have realized this as a voltage controlled current source in incremental feedback, right? Now if this is the case, what will happen? Okay, so we know that, so for example, first figure out the gain. What will be the gain? Which is V out by V in. Okay, so you know how to figure out the gain. You will first draw the incremental picture. So let me put it here. So I have V in and I have a current source, but this current source is not connected to the ground, rather it's connected to some RS. Okay, and some VS is there. Okay, and the output, this is my output, and I have a load connected to ground. Okay, now this is GM V in minus VS. Okay, so it's not GM V in alone, it's GM V in minus VS. Okay, so what will happen? So essentially this current, if I say this is my I out, this I out is the current that flows here. Okay, so VS by RS is equal to I out, and this then my V out is equal to negative I out times RL. Okay, and then I will have to figure out what is my gain, V in by V out, from these expressions. So GM I out itself is GM times V in minus VS. Okay, so substituting things from these three expressions, I can easily calculate what is my I out by V in, first of all, which is GM by 1 plus GM RS. Okay, and this is essentially the transconductance value of the amplifier. Okay, and if I multiply this by RL, I am going to have V out by V in. Okay, so V out by V in is this number essentially. So negative of GM RL divided by 1 plus GM RS. Okay, we know this, we have derived it multiple times, so it's just a recap. Okay, so what I want to convey here is that, let me put the expression here, AV is equal to negative of GM times RL divided by 1 plus GM RS. Okay, now let me take the GM common outside. Okay, so it will be negative RL divided by 1 over GM plus RS. Right, now you see what basically this says. You can develop an intuition from this expression that if you have a common source amplifier with source degeneration, then the output is given as, see, first of all, whenever you are looking at some out, or the gain, essentially whenever you are looking at the gain, the numerator will have the load resistance. Essentially here the load resistance, I have talked about RL, but this is anyway RD is RL. Okay, so the numerator will have RL. Okay, because if it is a amplifier and then you are talking about the output at the drain, then whatever resistance connected to the drain to the ground will come in the numerator. Okay, and in the denominator, you see you have two resistances that are added. One of the resistance is RS, and the other one is basically 1 over GM, which is the transistor's resistance. Okay, so you look in from this side, the source side, whatever resistance you see, which is RS plus 1 over GM, right, in series, that will appear as the denominator essentially. Okay, so you look at a common source amplifier with source degeneration. You need not go through this complex calculations every single time, because if you want precise analysis and more accurate answer, you can always go through it. But looking at it, you can always intuitively say that your output should be RL, which is the load from output to the ground. Incrementally this is ground, right? So that will appear in the numerator, and then the denominator, see, whenever you have a load, that will appear in the numerator. Okay, and the denominator will have the series or the resistance, equivalent resistance looking up from the source side. Okay, so which is RS plus 1 over GM. Okay, this is very straightforward. So this way you can actually come up with answers for all the circuits. Say for example, now given this idea is known to you, okay, so how would you solve this circuit? Say I have some transistor where I have V in here, and I have, say, let me call it M1, and let me call it RD or RL rather. Okay, so this is VDD and this is V out. Now instead of a resistance, I have a PMOS transistor, okay, whose drain is grounded and the gate is also connected to ground. Okay, which is a diode connection anyway. Okay, so how would you solve it? You know that this transistor has, so let me call it M2. This transistor will have an equivalent resistance, because diode connection transistor is like a resistor. Okay, so it has a resistance of GM1 over GM2, and this transistor will have a resistance of 1 over GM1, and I can write V out by V in by inspection. I can see this and write. I will not do any calculation. So first of all, my load resistor will come in the numerator from output to the ground node, and then in the denominator I have, looking in this side, what is my equivalent impedance, okay, which is nothing but 1 over GM2 plus 1 over GM1. Okay, it's as simple as that. Okay, this is my gain. So you need not calculate it every single time. So once you know the quiescent operating points of the transistor, GM1 is known, GM2 is known, RL is anyway given to you, you can calculate the gain very easily like this. Okay, so let me put you another, let me give you another question in the same area. So this is question number 5. So let me say that you have a transistor, you have a current source driving a transistor V in, and then you have a source degenerating resistor, and then you have V out taken from here, and is of course biased with some V bias, and this is VDD. Okay, and let's call it I naught. Okay, so how would you estimate it? Okay, first of all, if I naught is ideal, if I naught is ideal, what is the gain? Okay, so how would you do it? So if you look at the circuit for a minute, you would easily get the answer. Okay, by if you have proper intuition, you can actually get the answer. But then, first let me go about the roundabout way, like how to put the equivalent resistance and equivalent incremental equivalent, and trying to arrive at the answer. And second, I'll tell you how intuitively you can solve it very easily. See, first of all, if you go by the method I just told you, AV will be in the denominator. It's very straightforward, RS plus 1 over GM. Okay, but in the numerator, what will you put? It's if it is not ideal, I would put R naught of the transistor, and this is going to be my gain. But if it is ideal, in the numerator I have infinity. Okay, so I am not going to have infinite gain, then something will limit my gain, right? So I will have to see what is that. Okay, so this R naught is this current source I naught who's having a parallel resistor R naught, if it is non-ideal. Okay, but here the question is, if I naught is ideal, what would you do? Okay, so this is not the gain if this is ideal. Okay, in this case this is not the gain. Okay, so how would you proceed? So let's put down the equivalent picture. This I naught will go away. So at the drain, you just have your transistor, and a resistor RS, and you have the drain terminal, which is where your output is taken, and at your gate you have some Vin, okay, from this terminal to the ground. Okay, now as I said, if you don't have this current source, which is Gm times Vin minus Vs, okay, this is your Vs, right? If you don't have this current source flowing into anything, then you are supposed to imagine some R0, right? Otherwise you cannot solve it. Okay, so this R0 or RDS is the transistor's own conductance. Okay, output conductance, or sorry, output resistance. Okay, so how would you solve it? So first of all, you have a relevant node here. So you have two currents flowing like this, and one current flowing out of this node. So so you can write the KCL equation at node S. Okay, so you will have Gm times Vin minus Vs plus Vout minus Vs by Rs equal to Vs by Rs. Okay, sorry, Vout minus Vs by RDS, or let me call it R0. Okay, just to avoid any confusion, let me call it R0. Okay, this is Rs and this is R0. Now the question is, how would you proceed after this? Okay, it's going to be really difficult obtaining an answer, because this Vout is from this point to the ground, and we have a situation like this, and you cannot obtain any other equation from here to solve it, because I want everything in terms of Vin and Vout. Okay, so I want an expression for Vs that would connect me to Vin or Vout. Okay, so I want to represent Vs in terms of Vin or Vout, and then I can get Vout by Vin. Okay, that is what I can do. But then this is a roundabout task, and you can always see, and this is a simple circuit for which you will have to spend this time, but there can always be complex circuits. Okay, that like op amp circuit that we will see. Okay, in that case, what happens is that you have much more complex. Say for example, you have a block, and you have more number of transistors in the block, and each transistor will have its own incremental equivalent, right? And for all the incremental current sources, okay, you cannot keep on putting them in series and trying to find out what will be the node voltage and all these things. Rather, for the whole box, you want to have some kind of a for this whole box, black box, I want to have some kind of a current which will be determined by some Gm times the Vin, input voltage, and some kind of a output resistance Rout. Okay, so that I will calculate my Vout. So looking in this side, I should know what is my Rout and the Gm of the box. Okay, this is something that I want to know, so that I can easily calculate my gain. Okay, if I have this situation, I know very easily to calculate the gain. It's Gm times Rout. Negative of Gm times Rout will be my gain. Okay, so how do I do it? It's very straightforward. You take any box that you have. Okay, here in this case my box is this one. Okay, so you take any box that you have, and you have some input to the box, and you have some output node. Okay, so you short the output node to the ground and find out the Norton current. Okay, so you find out the Norton current, and let's say it's flowing in this direction, because here I want current flowing like this. So let's say I will find my Norton current flowing in this direction. Okay, and you calculate In by Vin, which will give you your Gm. Okay, and take the same box, you short the input node. Okay, basically deactivate the supply. Okay, and you look at things from the output node and calculate what is my Rout. Okay, this you have done multiple times. You supply some test voltage V test and measure I test, and V test by I test would give you Rout. And once you know these two values, then you can substitute in this expression, I mean in this particular circuit equivalent, and you can always arrive at the answer. Okay, it's very straightforward. So if you do this for this particular configuration that you have, let me tell you what you will get. So if I short this terminal, output terminal, to the ground, and say this is my Norton current. So this is no more V out, I have 0. Okay, so V out is not there, I have 0, and Vs is anyway there. Okay, so it's now has become simple. Okay, and this Norton current is the same current that is flowing in this transistor. So Norton current, this resistor, so Norton current is equal to Vs by Rs also. Okay, so Vs by Rs is nothing but my Norton current. Okay, so Vs is equal to In times Rs. So you substitute Vs as In times Rs and find out In by Vin. Okay, so I'll get Gm times Vin minus In Rs minus In Rs by R0 equal to In Rs by R0. Okay, so from here I just want to find out In by Vin, which is equal to my Gm. Okay, so I would get this value as, so this is Vs by Rs, I wrote it as In Rs by Rs, not R0, so they will cancel out, it's just In. So we will get an expression of Gm by Rs divided by Gm plus 1 over R0 plus 1 over Rs. Okay, you can verify it, this will be the expression that you will get. And now I have to figure out my R out. This is my Gm. Okay, now figuring out R out is also very straightforward. So let me put the incremental equivalent for R out. So if I want R out, then first of all my input should be grounded. Okay, and this will become a current source in this direction of Gm times Vs, where this is my Vs. Okay, and I have a resistor, a value Rs. Right, now why did I put like this? Because Gm times Vin minus Vs, and Vin is anyway 0 volt and Vs is negative, so I reverse the direction so that it becomes positive. Okay, so I have R0 here, and this is my V out terminal, and looking in from this positive to negative, what will be my R out? That's my question. So you put a test voltage here, V test, and then between this and ground, and measure what is I test. It's very straightforward, just like what we did. And if you calculate, then you will have I test is equal to Vs by Rs. Okay, and also you will have I test to be equal to V out minus Vs by R0. V out is nothing but V test. Okay, so V test minus Vs by R0. This is the current flowing here, and you have current flowing in this way, which is negative of Gm Vs. Okay, so and you substitute the Gm accordingly here, then you will get V test by I test as R out, which is equal to 1 over R0 plus Gm plus 1 over Rs. Okay, so this is going to be your, so this is essentially your into Rs times R0. Okay, so this is your R out essentially, and this is your Gm. Right, now if you substitute in this equivalent network, and you are going to have your gain, which is nothing but minus Gm times R out. Okay, which is equal to, see this idea of converting any particular, here it has only one transistor, but there could be number of transistors. But then even though there is one transistor, it's in a complicated situation. But if there are number of transistors, then also you can use this method to represent a single Gm and a single R out for all the transistors. Okay, which will be very, very useful. Okay, even for op amps we can do this. Okay, that is what we have done. So So this AV is here it is given as this and this, the product of these two. So you see this denominator will, this numerator will cancel up with this denominator, and this RS and RS will get cancelled, okay, and GM/R0 will remain, negative of GM/R0 AV, okay. This is what the actual gain is. Now you should have a question. The question is, if you see the first question that I posed you was to have a current source like this, and you have a V in here and V out here, and this is VDD, which can be incrementally grounded, and this is actual ground. In this case, this is the first question, and we saw the gain is nothing but AV is equal to minus GM/R0, and that is how we started the question answer session. And we said that if you don't have a load here, then you are assuming a load of R0. That is the RDS of the transistor. Okay, so here you have an RS, and still you are getting minus GM/R0. That means this RS is having no impact. Okay, that is the idea. That is the meaning, right? And so why this RS is having no impact is something that we'll have to answer. The reason is, see, look at this circuit. That's why I said if you look at it for some time with inspection, you can come up with the answer. So if you look at this circuit, essentially this is the constant current source I0. Okay, so this constant current source I0 is flowing through this ID as well as RS. So this I0 is flowing through this transistor as well as through RS. Okay, now because this I0 is established because of the bias. Okay, even when this Vin is not there. Now because of Vin, what will happen to the current? The current will not change in RS, right? The incremental current will not, basically there won't be any incremental current through RS essentially. So whatever may be the signal that you apply to the transistor, there may be some incremental current, but the idea is, as long as you have this DC current flow, because see, say for example you think of incrementing this node by some 0.1 volt, then also the current is going to be I0. Okay, see, say for example I have a bias voltage of 2 volt here. Now I give a bias of 2.1 volt, okay, incrementing slowly by 0.1 volt, even though if it is not a signal, then also the current through the resistor is I0. If I do 2.2 volt, then also the current through the resistor is I0, meaning for whatever change I do at the input side, this current through the resistor is not going to change, meaning it doesn't respond to the increments. Okay, so it's like saying the ground is actually here. Okay, meaning there is no current, no additional current that is flowing into this RS in the incremental picture, okay, than what it was flowing in the DC picture. So as far as the incremental picture is concerned, this RS need not be there at all. So if you find a situation of a common source stage with the source degeneration, which is directly connected to a current source in series, which is an ideal current source, then you can think of it like in incremental picture no current will flow through this resistor. So this resistor can be treated as incremental ground. Okay, so in that case you will still, in that case this and this are the same, and that is why you get minus GM/R0 here also. Okay, so in this, you can see this as an intuition and then come up with an answer yourself. Okay.